In this video, we're going to investigate a simpler means to calculate the torque than we saw in the last video, where we calculated the torque using explicitly the cross product. In this one, this is basically torque no calculus. And very often, this represents the most straightforward and simplest way to get at the answer. But at the end of the last video, we talked about how the torque serves to pick off perpendicular components. So what do I mean? Well, the cross product between R and F serves to tell you either how much of R is perpendicular to F or how much of F is perpendicular to R. We're going to take care of that in just a second by resolving these into components with other means. But let's talk, first of all, let's say when we're going to do this method, we treat everything as scalars. We're not explicitly calculating anything with vectors. That's okay. What that means is we're going to have to get the direction of the torque by inspection, by other means. Part of the advantage of the full calculus treatment is that whether the torque is negative or positive just comes out of the treatment and tells you which direction the rotation it tends to produce will be. For this one, we're just going to have to use our smarts and inspect it and figure it out. But usually that's not so bad. So let's look at this one. I basically even need the same system as I had in the last one. A bar that I'm gonna calculate the torques about this point, or just torque is just one. So I've got a force acting on the bar at some angle of 30 degrees. Let me pick off the parallel, and I'll call this F. I said parallel. I meant perpendicular. I'll call this F perpendicular. Perpendicular to what? Well, perpendicular to the R vector. So even though I'm not using the full calculus treatment, I still need to have a good understanding of where the R vector is and what it means, and it's always helpful to draw it in if you can. So there's the perpendicular component. The parallel component is going to look something like that, right? Where the blue is F parallel. So I don't know how easy that is to see. I think you can see it. So the green is F perpendicular, the blue is F parallel. All right, what do these things do? Well, first of all, let's look at F parallel. And let's ask ourselves, how much torque is this going to provide about this point? If you think of this as a door, think of that you're looking at a door from above, and this is the hinge. And you walk over to the door, and you grab the doorknob, and you pull away from the hinges. Or maybe you push on the door towards the hinges. I mean, if you're sitting in a room with a door, go do it. Does the door open? No. No, it does not, because this force, the line of action of this perpendicular force, the line of action of this parallel force passes through the point of about which we're calculating the torque. Let me say that again. This component, the parallel component, has a line of action that passes through the point about which we're summing the torques. You can't open a door by pushing towards the hinges. That is not how doors work. Right? That's what F parallel is doing. Although, as I've drawn it, you're pulling away from the hinges. Doesn't matter. Door's not going to open. Right? All right. What about F perpendicular? Well, if this is a door, then of course that's going to open the door. That's going to swing the door in a counterclockwise direction because it is perpendicular to this R. So remember, the cross product serves to pick off perpendicular components. If we can do that some other way, say by the vector resolution using trig we've been doing all semester if you're in my class, then we can maybe get by without using the calculus here. So just by resolving this force into components, which I certainly hope we all know how to do by this point in the semester, again, if you're in my class, by doing that, we're able to say that, you know what, F parallel provides no torque. I can forget about it. F perpendicular does provide a torque, so I need to worry about that. And of course, F perpendicular is, with theta here, is going to be F sine of theta. Now, let me say a word of caution. This sine of theta seems, you look at this and go, oh, well, that matches up perfectly with my definition of the cross product, because there's a sine of theta in there. Be careful, because theta was defined here arbitrarily. It could have been listed here, in which case the perpendicular component would be F cosine of theta. This is not the same theta that is in the cross product. Remember, that's a really specific theta measured from R to F counterclockwise. This is an angle theta which is probably always going to be between 0 and 90 degrees and is given in the problem statement. And whether or not you have a sine or a cosine appear here depends on where they put this angle. So don't let the similarities here make you go, oh, this is exactly like calculating the cross product with calculus. It's not. This comes out of trig. This is a vector resolution. It happens to look the same in this case, but it won't always. So be very, very careful. All right. With that said, I can say that the magnitude of the torque produced by this is F perpendicular. That really should have been a subscript. Let me just do that again. The torque, magnitude of the torque, let me just say this, is F perpendicular times the distance between the point of summation or the point of calculation, however you want to say it, and the point of application of the force. And so that's just going to be R, the magnitude of that vector. In this case, I'm going to get F sine of theta times R. So we've picked off the amount of F that's perpendicular to R, the component of F that's perpendicular to R, to be more specific. We've multiplied it by that distance, and I then get the magnitude of the torque produced by this force. All right, we've got the magnitude. What about the direction? Well, if I can say now that torque, if I want to treat it like a vector, it's going to be, I'll leave off the vector symbol. Torque is going to be F sine theta R. Now let me ask myself, what sort of rotation, if this force were acting and it was free to rotate about this point, I'm not saying it is rotating, it is free to rotate. If it were, it's a hypothetical, right? Imagine that this force, and if there are other forces acting on it, forget about them. I'm going to imagine that we're just worried about this force. And if it's free to rotate about this point, what sort of rotation would this produce? Clockwise or counterclockwise? Maybe we all see just instinctively that if I push up on this pin, it's going to rotate counterclockwise. We define that as positive. So that is a positive torque. A positive torque will tend to produce counterclockwise rotation. A negative torque will produce clockwise rotation. So of course you don't have to write the positive sign. I just did. But you do have to write the negative sign if you find that it's negative. So in just a few steps, we've actually avoided doing most of the calculus. Now, am I suggesting that you don't need to be able to do the calculus? Absolutely not. May it never be. Do not assume that I'm saying you can't do the calculus. If you're in my course, which is University Level Physics 1 at Auburn University, calculus is required and expected. You do need to be able to treat the full version of this with calculus. With that said, you will do that much more when you get to an upper level mechanics or an engineering dynamics course than you will in this course. In this course, usually the problems that you're set are more straightforwardly solvable with this method. And so we're going to do a lot of this. You might have to do some calculus. I'm not saying you won't, but we're going to do a lot of this. And I think this gives you a good understanding of what torque is and what torque does. It depends. It takes into account where you apply the force, not just the force.